Okay, so I'm going to do this little video about the lldb bug that I found just while it's fresh in my head so I can kind of remember it. Basically, I'll just talk about what it was, how I found it, how I fixed it, stuff like that. It started out, I was just doing some coding for fun. I was working on this string implementation and string dot, I think H, it's all in H. Working on this string implementation, and basically I ended up having this bug. Well, yeah, this kind of bug where in the copy constructor of the string, I basically would do the std copy to copy from the other string, and the pointer, the source pointer, was actually null, and so that caused a crash. And so if we go here and run the driver, it crashes, and so we can look at it in lldb. On my lldb sys is just user bin. lldb is the system one because I also have the a one that I built, and that takes precedence in the search path. So at the time I was just using the system lldb, and if you run the program in lldb, you see that there's this crash, bad access in platform mem_move. Okay, so that makes sense because it's in std copy. If we do the backtrace, you can see that yes, copy mem_move. And the instruction is this dereferencing RSI. So if we look at RSI, it's 0, and so that's a null pointer dereference. You can also see that here, address equals 0. So I wanted to basically just kind of, I was curious how this kind of whole mem_move thing worked. I wanted to see a little bit more how it got here. So I wanted to break at the first instruction of mem_move, and so I set a breakpoint there. And then what was kind of interesting is if you run it again, it doesn't hit that breakpoint, even though the breakpoint is definitely set at this A53EO or A5EO address. It's set. It does not get hit, and that was a little bit weird. Yeah, we can just run it multiple times. It always gets to that crashing instruction. It does not hit our breakpoint, and so I still wanted to kind of step through more closely in the instructions above, and rather than, I guess, just setting a breakpoint somewhere in the middle and trying to figure out where it actually happened, I decided to go up a stack frame and try to step in to mem_move. I never actually really did figure out why it was never getting hit because I got too distracted by this bug, whatever. But that was kind of the initial way I got started with this. And so basically, I think it was something like I set a breakpoint in this copy, and so if we're here, and then if we disassemble the function, wait, we need to rerun it probably. So, actually, it was something more like if we have this stack trace, and if you go up in the stack frames, it'll show you, where things dropped off, and so that's the user code. And now we're going into copying, and I guess there's this internal copy thing. And now we're about to hit the mem_move, and so if we disassemble here in this internal copy, we can see that it this is where mem_move is copied, or this is where mem_move is called. And so let's set a breakpoint here from the outset and then try to step into it, was what I thought. And so we can run it again. Nice, now we hit our breakpoint. right before the call to memmove. We disassemble. We're in copy. We're about to call into memmove. And so let's start stepping instructions. So we call into this, and what I found is that this is actually not directly memmove. It's just, this is like we're now at this indirect jump instruction, and so now we're inside of some kind of like dynamic linker stub code. This is like I don't really know Mac that well, but this is basically the same. It works the same way on Linux, where you have the PLT, and so we have the stub. And so if we just keep stepping, eventually we should, get into memmove. And so this is some more stub code. I'm not quite really sure what's going on exactly. Now we're at this push Q R11, and then we do this other jump into dyld stub binder, which is, dyld is the dynamic linker on Mac. And so now, yeah, we're definitely in some like dynamic linker symbol resolving code. And if we just disassemble it, there's a bunch of code here. And when I was looking at this, I had no idea what was happening here. I just wanted to get back to memmove, hopefully. I wanted to, just get back out of this stack frame, hopefully, and kind of get back to where, the normal user code, not this dynamic linker code. And so, so I did a finish command, which is what I usually do, which exits, runs the function, then gets back, and then breaks back at the caller. And then what I noticed was something very interesting happened. The lldb said that the program suddenly crashed, but this is not the same crash that we had last time. Remember, the last crash was at memmove. It was like dereferencing RSI and stuff. This crash is totally different. We're crashing in dyld or dyld. I don't know how to say that. Fast bind symbol at this move instruction. And the most interesting part of this is how the crash happens. And so we're dereferencing RDI. If we look at RDI, it's hex CC, and it also says that up here. And so the program crashes because it's trying to read from hex CC, which is such an interesting crash. I've never seen this kind of thing before. Usually you might see like a null deref or something, but this is a hex CC deref. And what's so interesting and suspicious about this is that hex CC is the opcode on x86 for software interrupt. And so when a debugger goes to implement breakpoints, it actually injects these hex CC instructions into the code such that when the code hits, it'll trigger a software trap back to the debugger, where the debugger can get control again. And so it's just pretty fascinating that we're crashing at hex CC, because this very strongly points to the fact that it might be a debugger bug. And these things I've never really run into a debugger bug before in this kind of way. But this, strongly seems like there's a bug in maybe the finish command or something going on, where a hex CC gets written somewhere weird that results in a non-legitimate crash. This is a crash caused by lldb. It's like a crash caused by a bug in lldb, essentially. And so I got completely sidetracked from everything I was doing and just investigated this a little bit more deeply. And so if we look at the backtrace for this, we're in stub binder, which calls into fast bind symbol somehow. And yeah, so at this point in time, I didn't really know exactly what was going on. So one thing that was also kind of interesting is that so I'm just going to set the breakpoint in dyld stub binder, because that's really the interesting part, and I'll disable the breakpoint in basically everywhere else. So now if we run it again, we directly are in stub binder, but we're still kind of in that same path that we were in before with the copy. And so if we do the finish, we crash in fast symbol at the fast bind function. But otherwise, what if we just continue? If we continue, we hit the original crash. This null deref and mem move. This is the original crash we were looking at. And so continue behaves differently. But if we're at here and we do finish, it's reproducibly crashing at hex cc. So that's interesting. So the next thing I thought it would be interesting to do is kind of, I guess, try to step to this crash to see exactly how it was happening. And so we can try breaking at dyld fast bind symbol and stepping to this instruction and and seeing exactly how the CC crash occurs there. And so if we do that, we can run it again. We're here. Actually, we'll set another breakpoint. And so basically, all this code runs, and it's actually at this point, this call right here into dyld fast stub entry is where kind of it starts going into the fast bind symbol thing. And so we'll set a breakpoint there. So so now we're at dyld stub binder. We're just going to continue a couple instructions down function right before the call in there. We'll continue. Now we're at the start of fast bind symbol. And let's just start, I guess, actually, yeah, well first we set the breakpoint on that crash in fast bind symbol. It's, I believe it's this one. Yeah, fast bind symbol plus 67. And so if we just continue to that, we're going to stop there. And, we should be about to crash with hex cc because that's kind of where the crash was. But if we look at RDI, it doesn't have a CC anymore. We're not going to crash. And so if we step one more instruction, it's fine. It's totally fine. And we can try again. We can go. So now we're at the start of fast bind symbol. We can just step all the way down, through this code. I don't think it should take too long to exactly get there. But eventually, pretty shortly, maybe not. I actually haven't done this part too much before. Actually, yeah, I guess here we are. So we just stepped literally all the way into the function, and now we're at this. So we set a breakpoint at plus 67 at AB63, and that's where we are right now. So we basically just manually single stepped all the way through fast bind symbol down to this crashing function. We should be about to crash now, but the same thing happens where if we look at RDI, it's not hex CC, it's a perfectly valid pointer. And so that's also very interesting about this bug. The crash happens during the finish command at this certain instruction, but if you just continue, for one thing, you're not going to hit that crash. And also, if you single step to the instruction where the CC crash happens, it disappears. It does not crash there. So this is a second thing that points really strongly to the fact that it might be a debugger bug. Interest is very piqued at this point to kind of explore this some more. And I think the next thing I did was I wanted to actually take a look at the code to kind of see what was going on here. And so basically I started like disassembling dyld and stuff. And so I believe Yeah, so dyld stud binder is in a different binary, but this fast bind symbol is just in dyld, and so which or I think it's user bin die or where is it? User lib dyld. That's it. Yeah. So if we disassemble user lib dyld and start looking at this function, which is fast bind symbol. Oh, wait, that's why. Sim dyld fast bind symbol. Okay, so now we're here. And if we look at it in graph mode, it's a bit easier to read. So this is the instruction. Yeah, so this is the instruction. It's this move from RDI into racks. And that's where we were, right? Move, yeah, at this hex 67 offset into the function, followed by this LEA. And so, right. And so basically, RDI is what is being has the CC in it, and so it's kind of interesting to follow that code path. This is actually not a really big function; it's just a couple basic blocks, and basically what I found is that the path that needs to execute is kind of it cannot come through here. Well, basically it tests if RDI is null, and if it is null, it goes to here. But if it's not null, it goes down this code path. And then RDI is uninterrupted or whatever, and then it's dereferenced here. And so in order for that path to RDI to have a CC at the crash point, basically the argument to this function RDI is a pointer to a hex CC. And so in RDI, if a pointer to hex CC comes in through RDI, we dereference that pointer and get the hex CC here, and then test if the hex CC is 0. It's not, and so we come down here, dereference it, and crash. And so, so we know that fast bind lazy symbol is getting a pointer to hex CC as a first argument. That's kind of interesting. I think I was also disassembling this dyld stub binder function, which isn't a different thing. It's in like lib_dyld or something like that. Yeah, lib_dyld.dylib. And so if we lib_dyld system, yeah. And if we go here, basically, yeah, so this is the same code we were looking at before. We step down a bit, we can see that we have this call to dyld fast stub entry. I don't exactly know how dyld fast entry gets into fast bind symbol, but I think it's like a very thin layer before a fast bind symbol. And what's kind of interesting is that you can see right before the call to this function, it's being set up with two arguments, one in RSI and one in RDI. Basically, at some point I had this like idea, or I guess insight, that in order to implement the finish command in the debugger is going to go onto the stack and find the return address that the function is going to go to after it's done executing, and then basically it's going to try to write the breakpoint there. Or I had this other dumb idea that the debugger would smash its own, like smash the stack of the program and put a pointer to CC there or something. But it basically finds the return address and writes a breakpoint there. And so what was happening here is that for some reason, the return address was not in the place the debugger was expecting, and so the debugger was just taking this other random pointer and writing a breakpoint, and dereferencing it and writing a breakpoint there. And so that's kind of what my theory was, and it's a little bit interesting. And I was able to confirm this by just kind of reading through dyld stub binder code. But if you just like Google for it, you can find it on GitHub. It's like an Apple's open source kind of thing. It's actually like handwritten assembly, and what is unique about it and what caused this bug is that it doesn't use a standard stack layout. In particular, it receives arguments on the stack, which is a little bit unusual, which is highly unusual for x86 or x64. And so typically, your first like 5 arguments go in registers or something like that. But this function actually takes arguments in registers or on the stack. And those arguments are what is being mixed up by the debugger as a return address. And so if we go back here and we look more closely at stepping into, so I'll actually re-enable the breakpoints, and let's watch as we step into dyld stub binder. And the breakpoint need to re-enable is probably breakpoints 2 or 3. Does that work? Okay, yeah, that works. Okay, cool. So now, yeah, great. Now we're about to call into all that dynamic linker stub code. So if we step, dynamic or indirect jump, and then pushing hex 5b onto the stack. Okay, that's kind of interesting. And then pushing when we push R11 onto the stack, and then jump Q. And so dyld stub binder is expecting some arguments on the stack, and actually, I guess look right here. So it's expecting a thing on the stack, and that thing is actually a pointer, because we do a LEA into R11, so R11 is going to be this pointer to something, and we push that on the stack, and then we jump. And so dyld stub binder is expecting to find this pointer on the stack. And we haven't done the jump yet, and so if we regread R11, we can see that it's this kind of like random pointer. And so we step one more time, and now we've arrived in dyld stub binder. And if we look at our stack, which is, well, I have this hook that does it, but for XG RSP, we can see that there's that R11 that got pushed on the stack. And if we go back to our disassembly, so RBP, what is interesting is that, right before the call, we do RBP plus 8, and then RBP plus 16. And so this, at the top of this function, it pushes RBP. And so RBP is at the bottom of the stack, and then it swaps, and it sets, then it moves RSP into RBP. And so basically, to access that R11 pushed pointer, that pushed pointer is going to live at RBP plus 8, because the 8 is going to be the pushed RBP itself. And so actually, so basically what's happening is that dyld stub binders has a non-standard stack layout where it's accepting this pointer argument on the stack, and then it's forwarding that pointer argument into dyld stub fast entry, and it does that right here because it loads at RBP plus 8 and moves that into RDI. And then in somehow a little bit later in dyld fast symbol, we get this pointer argument RDI and then use it. And so basically what's happening is that we're sitting at a breakpoint in dyld stub binder. We have our R11 data pointer sitting at RBP plus 8, and then we do the finish command. The finish command looks at the stack, and there's some, I don't quite understand it, somehow it incorrectly guesses or assumes that the return address is going to be at RBP plus 8, because that's actually where it kind of typically is going to be for a function with a normal ABI which has been called into, and so it's going to take that return address that candidate return address that it found, and it's just going to write a breakpoint, follow it, and write a breakpoint there. But in this case, we have this data pointer, and this data pointer on the stack, and it's just going to write the hex CC at that data pointer. And so basically, by the time, and then it's going to continue execution. And so it's going to do that. If we do that finish at the start of dyld stub binder, it's going to basically take that pointer on the stack and make it a pointer to hex CC. Technically, it would just write a single byte, but in this case, I believe the pointer pointed to a null pointer. I'm not recording anything but my terminal right now, but if you go on Google, you can see some comments, I think, about how it takes like a double pointer or something. We can actually just also look here, but I believe R11 is still that pointer, and if we dereference it, yeah, we can see that it points to just a big null. And so the debugger is going to write a hex CC here, turning this into a hex CC. And so basically the debugger basically corrupts the memory with the breakpoint and then continues execution. And so by the time we hit this call, this RDI is going to be a pointer to hex CC. And then that crash is going to happen. And so, that's basically the bug. There's no validation on that return address. I mean, it's a little bit difficult to generically detect if it's if it's actually a return address or if it's just a random pointer. But one really simple check you can do is just to see if you're writing into executable memory, because there's never a situation where you're expecting to write into read-write memory, because you're writing literally a breakpoint instruction that you're expecting to be executed. And so you're definitely going to want to make sure that the return address points to executable memory. And that was basically what I found, what I determined that a simple check would be to fix this. And so I downloaded the lldb code and stuff and started working on a patch for it. And I could show that over here. And so basically I have lldb's code up here, and this is the relevant file basically. So thread plan step out is what code controls the finish command, because the finish command is actually an alias for thread step out or something. Technically thread step out is the real name of the command. And so there's this whole really interesting thread plan infrastructure that they have. But thread plan step out is the code that implements the finish command, and specifically a lot of it is implemented in the constructor. This whole looking for the return address and writing a breakpoint is all in the constructor, which is kind of interesting. basically, yeah, it happens. Yeah, down here. Maybe I will check out to master and show you the original code first. And then, so if we, yeah, so this is without any of the code that I wrote. And yeah, we have this return breakpoint thing, return address, something, something, something. So return address, return address, return address. And so yeah, basically there's this some code, it does some kind of check about an inline frame. I don't know what that is, but otherwise this really is kind of the interesting block. We have this frame object and we get its code address or something, and then we get this return address, and basically this if statement doesn't really execute as far as I've seen, and then this return address is like this capital A address object, and so we do this get load address thing to convert it to a like a UN64T kind of thing, and then we check if it's an invalid address, but if it's not, we just directly go and write a breakpoint there with this function create breakpoint at return address, and that is the code that has basically the issue, the bug. There's no validation here, and so all I did was I added some validation. And so basically we can do this get load address permissions call, which gives us the permissions for the page where this address is, and then we make sure we get that, and then we can check it if it's executable, and then basically the way, since this is the constructor of the object, you just return. The only thing you can do is return, really, and the way the error is handled is if you return here, the constructor will not have this return breakpoint ID thing set. It's going to be its default value of invalid break ID. Right here, it gets initialized to invalid break ID, and then if everything goes well, it gets initialized to this value. And then later on, in this validate plan function, that's where this kind of the state of the object is checked to see if it initialized well, and if it didn't, that's where errors are thrown. And so basically, yeah. And then so if this thing is LVM invalid break ID, that means the constructor did not really run correctly. There was an issue, and then and then we return false to signal there was an issue. And so basically, if we go back to this program, and then so just lldb on my system corresponds to the lldb I've built, which has the fix. And so if we go back here, and we'll just show, if we just run it normally, we hit the mem move, and then if we break on dyld stub binder and rerun again, and then finish. So last time in the old debugger, this is going to crash on hex CC. Now it checks that could not create return address breakpoint, return address, blah 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 blah, does not point to executable memory, and we do not have a fake crash or anything. So yeah, that's kind of it. There's a couple other things to show. I wanted to also, so this is an example of lldb causing corrupting the program state, which leads to a crash. That's a fake crash, but there's no reason the program needs to crash because of this memory corruption that happens. If done in a certain way, this command could just silently corrupt memory with a CC, and the program could just keep running, but just with corrupted state, and it'll be and kind of be running incorrectly. So I wanted to have a bit of a just kind of a proof of concept of that kind of thing too. And so I yeah, I believe this bug too. And so if we look at it, we have this main CC. This is just an entry point, and then basically it's written in assembly otherwise. So then it links with func.s, which is where my func is. And basically what we need to just do is make sure we have a sub with a non-stack standard stack layout so that the bug will be triggered. So the lldb is going to confuse some pointer on the stack with a return address. And we just need to point that to something kind of benign that was not going to cause a crash later. And so what I've chosen to do is in the main.cc, it returns from main the return value of my func. And I basically have the program allocates and like a int on the stack and initializes it to 44, which is the random number I chose, and then pushes the pointer to that on the stack, and then jumps to this stub. And basically all the stub does is load that pointer from the stack, dereference the pointer and move it into racks for the return address, and then just return. And so under normal operations, if we run main, it should just return hex 44 as the return code. And yeah, like what is hex 68? It should be 44. Hopefully it's 40. Okay, yeah. So basically, yeah, if we just run main and look at the return code, it's hex 44. But then if we can trigger the bug, if we do a finish command at stub with non-standard stack layout, what's going to happen is that lldb is, so right now normally we have the pointer to hex 44 on the stack. And so lldb is going to see that pointer. It's going to write the breakpoint to the pointed to memory. And so it's going to write the breakpoint and overwrite the hex 44 with a hex cc. And then the program's going to continue. It's going to load that hex cc into racks and then return. And so if we run it in lldb sys, and we just break main and then start stepping. So we're stepping into my function, and then we set up the so we can see that we allocated the 44 on the stack, and then this pointer that we just pushed is just a pointer right here. And so we're about to do the jump into the stub. Now we're in the stub, and let's just continue. So we continue normally. Hex 44 is the return code. Cool. We let's go back there again. We're in the stub. Now if we do a finish, hex cc is the return code, which exactly kind of shows that what's going on. And so yeah, this is exactly what happened. So lldb corrupted that data that was pointed to, and then continued the program's execution. And in this case, nothing. It was not going to cause a crash because it didn't corrupt a pointer or anything. It just corrupted some normal program data that eventually, and the program continued with it. And so this is observable in this case as the return value. And so we return hex cc. One side note about this is that it would have been nice. It would have been nice to debug lldb itself and actually like step through watching it like set the breakpoint and corrupt memory and stuff. But it was actually really difficult to get that set up. You can load lldb in lldb. Well, I guess before I show that first, I'll show it with the fix. And so if we're here at main, we can break main, step into the stub, and then finish, and then it has the error this time. And so it does not incorrectly run the program. And that could be so bad. Like if you could, I don't know, it is a little bit of a niche situation you need to get in. But if you're a developer of like a dynamic linker or something, and or any kind of thing where you have like stubs, like these weird assembly stubs, maybe like programming language like runtime, people might have this kind of thing where you're trying to debug it, and then you just want to finish from your stub, and it corrupts your program in a non-crashing way, but that gives you weird results. That could be such an awful situation to be debugging, and that's why I think this might be why some people just don't like debuggers, because if you're just using prints, you're not gonna really have this kind of thing. But the debugger, generally is quite stable, but still there are these little kind of corner cases where you can get yourself into these little like weird situations where it might actually just corrupt memory and actually change execution. Hopefully, they're quite uncommon. This is a pretty, yeah, I haven't heard of this kind of thing really before, but theoretically it's possible. Debuggers can have bugs too. And so anyway, back to what I was saying with lldb. If you try to load lldb in lldb, let's see if this works. Well, first of all, in order to really make this work, you need to set up your lldb that you're going to debug such that it kind of runs without input, and so you need to make an lldb init like so. Yes, I don't really have one. This is not really going to do the thing, but maybe we can make it. So if we break sub with non-standard stack layout, and then finish. So lldb s lldb init main. I guess we probably need to run it also. Oh yeah, so we need to run it with lldb.sys so that it reproduces the bug. So we're trying to debug our buggy lldb, and maybe we'll just throw in like a -b so that it exits after it runs the script. And so now we've got our lldb running totally without user input, and so maybe because it would be insane to have like an lldb that you're using, but you also need to provide input to your like debugged lldb to get it to do what you want, and so you have to automate the client lldb that's being debugged so that you don't need to give it any input, and that's what we have here. It's just this lldb script that goes through, it sets the breakpoint, it runs there, and then at some point it does the finish command, and then the program exits with the CC. And so this fully reproduces like our bug situation, and then maybe in this case you can debug, run lldb on your lldb with those arguments, but of course that's not going to work because it's a shell thing, and then you can't debug that, or in my case, so you would have to debug your built one, which for whatever reason doesn't have the SIP protections or something, and so maybe this can work. I think you maybe need to put the -- or something, or maybe you need to, I think I put the -- in the wrong place. So you give it the path to the binary, and then after you give it or maybe you can just use these set args. File args. Is there a set args? Yeah. set args. Let's quickly Google this. Yeah, set args. No, settings set. lldb. Now this this thing should work. So put the maybe the main needs to be first. Yeah, there it was. Okay, so this is our lldb. That's debugging our. That's actually kind of interesting. Why we're still using the system lldb. Anyway, then we're debugging our main program and passing these arguments to it. And so actually, if we just run this, it's going to start lldb and run it with, I don't know, this is not exactly what I expected. I should have run the full thing. Oh, for some, expose that to main for some reason. That's not what I want. I want it to I'm just going to do it the other way. So lldb sys file user bin lldb, and then settings set run target args sldb init, no, main sldb init -b, invalid value event, or maybe just process launch main sldb init -b. Okay, so to which lldb? So which lldb will go to the one we built, which hopefully, yeah, which will enable us to attach to it. And so that took kind of a long time because lldb is kind of a big program. And so process launch main sldb init -b. Yeah, and so we, and then, yeah, right, it's not going to work. Well, it's not going to have the crash because we're debugging our built lldb, which has the fix. And so we would technically need to go back, for example, to this code and maybe just check out back to master, and then build, and then build. Hopefully this should be pretty quick. Yeah, so we're going to build an lldb without the fix, but is not in the system directory, so we can still debug it. And then we'll be able to maybe try to debug the debugger. But it's not. I'll show you why it's not really going to work, or why it's not really going to be usable. But basically, it's just we're going to want to, well, for one thing, there's an incredible amount of code that gets run in that like unwinding process of like figuring out the stack and stuff. It's just a tremendous amount of code to dig through to actually find exactly where the the setting the breakpoint stuff happens. So that's kind of one thing. Two, So I think our thing built 2. We can try this again. It's loading lldb with all the symbols and stuff. We'll launch it. So if we launch this now, we should see the hex cc hopefully return. Nice, yeah. And so yeah, we've just run an lldb within lldb, and the inner lldb, had the bug and stuff. And so maybe we would want to use outer lldb to break on the lldb, on the inner lldb, and step through it and watch it like set the breakpoint and corrupt the memory and stuff. But the second reason why that's pretty hard is, so now we want to set a breakpoint on some symbol within lldb, and so we'll use the break, and then we'll need to kind of like type in the name of the thing we want to break on. So maybe we want to break on this thread plan step out thing, and the usual way I would go about doing this is type in like a little bit of what I think is like the symbol name, and then use a tab complete to get me the rest of the way there. But I tab completed, I'm tab completing, and now everything is just completely locked up. Presumably there is just so many symbols or something that it's like trying to tab complete this, but I can't even do anything anymore. My terminal was just totally locked up. So that's kind of the second practical reason it was pretty difficult to do this. Maybe I could have not relied on the tab complete and actually typed out the fully like qualified name of that symbol, but it can get kind of, oh wow, okay, it can get that. Actually, I've actually never seen that return before, but I don't know. Yeah, either way, that that didn't really work. I pressed tab a bunch of times, but then yeah, that didn't really work. So so maybe you could be really precise and not need the tab complete and just type in the fully qualified name of the symbol. But that gets pretty difficult when you are dealing with all this C++ kind of stuff with all the templates and whatever. And maybe the actual practical reason why that also will not work, at least in this current invocation, is because of lldb's architecture, where it always employs a client-server model, where the server is actually the one that's forking the process or whatever, the child process, using the operating system's like debugging APIs, or like it would be ptrace on Linux, but I don't think Mac uses ptrace. So using whatever its own thing is to like write in memory and do stuff. And so on the client end, we're simply debugging the client end of lldb, and all the client does is send like these remote protocol packets over some kind of communication mechanism to the server. And so by stepping through the lldb client, we're not really going to see anything like that interesting or meaningful. We're not going to see the actual like memory corruption happen, really. We're just going to see it kind of invoking this. We're going to see it like sending this packet to the server saying like, please write the memory, please write this byte here or whatever, maybe. But and then we'll just see it like wait and then come back, get a response back from the server saying that it did it. And so maybe that could be enough, but that's not exactly what I was envisioning. And so in order to really get it working, you would need to fully debug the debug server, but that's really complicated. Apparently you need to there's this code signing stuff that you need to do it, or I don't know, do it on your own debug server that you built. But anyway, it gets pretty complex. And so for doing this, it's kind of I just needed to like, yeah, there was you couldn't really use a debugger to solve this. You just needed to kind of reason about it and find these little, I guess, like side channels, such as this, that little assembly program that uses the return, like this func s. This is like an example of like a side channel where you can kind of observe the behavior of what's happening without using a debugger. and so you observe it via the return, via the, I guess, the exit code in this case. But yeah, I think those are kind of the main things I wanted to talk about. This is probably a super long video at this point, but hopefully maybe you found it interesting. I'm for sure gonna forget everything about how this worked, pretty shortly. So that's kind of why I did it, just to remember it, document it, because it would have taken, like, writing a blog would have taken super long time for this, and so I figured just doing a video would be quicker. One kind of interesting thing that I discovered, and I actually am not really sure of the solution for this either. This is just a weird question, open question that I kind of found, is that I initially tried writing this program using only assembly without that like little C stub at the start. And it was basically the same program though, but it just had the global main symbol at the start. And if you build it to func.s and then use the system lldb on this func program, break main, and run, and then start stepping. So now we're in the step with the non-standard stack layout. We're using the old lldb. Using the finish command here should, crypt the memory and set the return code and stuff. But what I actually found is that it didn't work. This is the old lldb without any of my fixes, and it still didn't work in the case that purely assembly was being used. And I thought that was pretty interesting. And I haven't really fully understood why this happens, but I did spend some time looking into it, and so one of the reasons that it could be is because in this handwritten assembly file there is no debugging frame information, and so because of that, when you do the finish command, it's going to be doing some kind of debugging unwinding kind of thing to find out where that return address lives. But for some reason, it can do that even if it's just the same assembly program, but with this little C entry stub. For some reason, it can still do that, even though there's still no debugging information in that version because it's just the C stub. But in this version where there's no C stub, it's unable to basically like work at all. If we try this one more time, run it, jump, and if we enable some debug logging, like unwind and maybe break, and then try to do a finish here. This is the unwind debugging, and I don't really know how to interpret it, but it doesn't look like it's very successful. There's this message about invalid thing. And so basically I wrote a version of it with manually adding the debugging information to the assembly. And so bug2-cfi. And so now if we look at func.s, it's basically just the same program, but I've manually written in the debug info using these CFI directives. CFI stands for control flow information, which is not the same as control flow integrity. Those are different things. Control flow information is just this basic, it's just like these debugging directives that basically express for every instruction exactly how far away the the saved return address kind of thing is, it's actually this like CFA canonical frame address thing. But basically, it just enables you express, whenever basically the stack pointer is adjusted, you add another directive that tells how far it's been adjusted, kind of thing. And this enables the debugger for any arbitrary instruction in this function to determine how far away the stack pointer is, or I guess how to actually compute the canonical frame address given the current instruction. And so basically, yeah. So I manually written this in, and then if you compile it in here, and then do the same thing, now it has this debugging information enabled. And so we can run it and step into our stub and enable all that logging, unwind. And then, well, for one thing, if we just do finish, so the finish actually worked. So there's a couple things happened here. And so we got a lot more unwind output this time because of the debugging information that enabled it to successfully find the top of the frame. And we can also see that the finish actually didn't have the bug. The finish actually worked here. So now we are broken in like this start function, which is actually kind of the pre-main like libc code. And so because what's happened basically is we've successfully we have this main function and we've successfully finished from it and broken back at the outer code. And so the question is, well, why didn't that bug trigger with the hex cc? And that's because of this debug information. It's actually the program because we have correct debug information. When we are at this stub function, I guess the stub, the debug information actually directly tells it that the return address is like it actually tells it where the return address for main is. And so previously, without this explicit information for a handwritten assembly like dyld stub binder, the debugger was just kind of guessing about what was on the stack. But now that it has this information, it doesn't need to guess anymore. It can actually, because I've written these directives and actually written them correctly, it's going to use that information to correctly find that the return address is actually not that thing just pushed on the stack. It's actually this thing like a little bit farther up the stack that was pushed before main started executing. And so because we have this information here, it's actually able to correctly unwind the stack and identify where the return address is, set the breakpoint there, and actually do the finish command. Just one little thing we can do is objdump -u func or -s maybe. Yeah, this is the one that dumps the sections. We can see that we have this frame section, which is generated from those CFI directives. Otherwise, if we look at the original, it was just ASM. Without the CFI, we only have 2 sections. I don't really know what this unwind info is. It doesn't seem to be very helpful for this just SM case. But here we have the frame section, and that enables it to actually unwind things correctly. But for me, it's still an open question. So if we go back to bug 2, this is our tiny little, I guess, C++ entry point stub. We have this func.s, and it's the same thing. There's no debug information here, but if we run this in lldb, we break main, we step some more, we step into, and we hit our stub with non-standard stack layout, I would kind of expect it to break in the same way that the assembly-only version broke. Broke, not meaning debugger broke, but like failed. Like it failed in that version to unwind the stack. It failed to write the breakpoint. But if we actually finish here, it just like it somehow works incorrectly, but it was able to unwind the stack somehow and set a breakpoint. And I really do not understand what the difference is between that purely assembly version of this program and this version, which is basically the same thing, but just it has this little C++ entry point that was linked. But otherwise, should be exactly the same. But for some reason, this one is able to have better stack unwinding or something. I'm not sure if it's just because it's getting, the stack unwinder has kind of these heuristics and stuff. If we do image show unwind stub with non-standard stack layout, maybe, or image unwind stub with unstandard stack layout, we can see the unwind plans. And for this function, there's a couple of them. And if we actually, where are we right now? So if we have these unwind plans, and if we step into the stub and then enable unwind logging, and then for example just do let's just do a finish. We can see the unwind logs, and we can see it referencing the unwind plans. And it's using this default unwind plan, but it was trying the assembly instruction unwind plan, and then it was using the default unwind plan, and all this kind of weird stuff. So I have the sense that there's sort of these heuristics being involved. It's trying these different plans, and for some reason, in this case, it's working correctly, but for some reason in the other case it's not. One thing I've identified is that the starting state is a little bit different here, and so it seems to be starting with sort of maybe valid state or something here. It has these like this pointer to a saved PC probably when we're doing a finish here. But if we go back to the just assembly one and go to main and step to, I think step's too far. Jump into the sub with non-standard stack layouts. We'll also just confirm that the unwind plans are kind of the same. We have these 3 unwind plans. I think they're pretty much the same. And then if we, so now we're here at stub thing, we'll just do finish. And with the logging, so we can see that it has way less output, has invalid message, and it seems like the starting state of things was like weird or bad for some reason. It had like a 1 here, which cannot be right. So yeah, I don't know. This is just me rambling about this other thing that I actually was not able to understand exactly what the difference is between this purely assembly program and the same program with this tiny little C++ entry point in terms of the debuggability of them. Like what? I don't think it's generating. Well, for one thing, I don't think compilers can really generate the debugging CFI directives from handwritten assembly. I don't actually really know, but I think they can do it if they're compiling down from C because they have more information about how that whole process happened. But if it's just handwritten assembly, I don't believe that they can do it. So I think you need to write it yourself. And so it's not like for that thing with the C entry point, the compiler is somehow generating all these CFI directives for that still handwritten assembly. So I don't really know what else it would be. I mean, we can even kind of confirm this if we go to the CFI version, go to lld and debug it, bmain, and then if we do image show unwind, for example, main, image show unwind main, we can see that it has this frame unwind plan that it got from the data, and likewise, if we do the stub with non-standard layout and look at its unwind plans, we can also see an frame unwind plan. But if we do the same thing here for this just SM1, we would expect to not see those unwind plans. And so broken in main, image show unwind main, unwind main. Yeah, just our three normal ones, for a stub with non-standard stack layout, same thing. There's no frame plan here. And lastly, we'll go to just this thing, and we'll check if there, but there were no frame plans, I think, there. Bmain, and then show unwind image, show unwind and main. There's this compact unwind plan and fast unwind plan because main is the C++ generated code. But if we do myfunc, that's when we hit the plain assembly, and it's just the plain no nothing. And yeah, if we get stub with non-standard stack layout, same thing. There's no frame or anything here. So it's not like, I don't believe any CFI directives or debugging information was generated for that handwritten assembly code. But the question is, why is it still able to do this stack unwinding stuff? Although it's doing it incorrectly, but for some reason it's still able to kind of do it, which I am not able to explain. So yeah, I think that is roughly everything actually.